Hello.
Hi.
Howdy.
Sup. This is a very special Hugo Girl, the podcast, where normally we read Hugo Award-winning novels, and we have read The Forever War by Joe Haldeman, and it has a lot of time stuff, so we thought, let's get a time stuff expert, also known as a physicist.
We phoned a friend.
We did phone a friend. Well, what we really did was Skype a scientist.
Yes, which is a really cool program, and okay. Hi, Emily.
Hello, how are you guys?
Good. Thank you so much for joining us today
No
for
problem.
a session of Skype a Scientist, and you're going to teach us all of physics today, right?
Yeah, we're gonna cover everything.
I mean, we are self-taught scientists. Most of our education is through rank speculation after we read a science fiction novel. So I think we're going to pick it up pretty quickly.
Yeah, so you pretty much know everything.
Yes.
Yeah, we're
We're still excited to.
Yeah, we're also 3 former English majors. So.
Wow.
So you have a lot to work with. So why don't we, would you want to go ahead and just introduce yourself? And if there's anything you want to say about Skype a Scientist, please go ahead and do that.
Yeah, all right. Well, my name is Emily. I am a first-year graduate student at Brandeis University. I'm studying particle physics, and I'm working on the ATLAS experiment. So ATLAS is a really cool particle physics experiment at the LHC in Switzerland. And we are investigating all sorts of super interesting questions like what is dark matter, and why is there more matter in the universe than antimatter, and what are the fundamental building blocks of matter? So I am here because of Skype a Scientist, which is a cool program that allows classrooms and groups that just want to learn more about science talk to scientists. So if you have a group that wants to talk to a scientist, you should definitely check that out, and you'll get matched with someone who can tell you all about it.
Thank you. This was so exciting. I was looking at my email every second, and when we got matched, I was like, yay! I was so excited. And I want to let people know, too, that Skype a Scientist is free. Donations are encouraged, and we're excited to be able to make a donation after we finish our conversation today. We're definitely going to do that. But just want to let people know that it is a very accessible program. So if you have questions or have a group that has questions, this is something that's accessible to everybody.
Yeah, awesome.
Okay. So the matter and antimatter thing sounds awesome. So I might want to do a follow-up session on that.
Okay.
So the thing that prompted me to try to sign up for this, and I heard about it on Ologies podcast with Ellie Ward, which it's probably anybody who listens to podcasts listens to or knows about Ologies. It's funny for me to tell our dozen listeners, hey, there's a podcast called Ologies. But anyway, we heard about it there. And so one of our listeners, Emmanuel, asked or gave us a topic to discuss in the context of our current read, which is The Forever War by Joe Haldeman. And he asked, what do you think about the impact on relationships and how they're affected by relativity and time dilation? So in that context, I thought, maybe I should understand those things better. So that's sort of the overarching theme of the conversation today.
All right. Well, sounds good. We can talk all about time dilation. I do particle physics, and time dilation is something that is very relevant to what we're doing. So it's a super interesting topic. And it's, I think, crazy to think about that it's real and it's not just science fiction.
So is there a simple definition of time dilation?
So without understanding why it's happening, you can understand what's happening pretty easily. And that is that time is moving slower for someone who is moving really fast at speeds close to the speed of light.
Nope. What?
So.
Go, Amy, go.
Just say that one more time slowly.
So if you are standing still and you have someone who is going really fast at a constant velocity, you'll see that their clock, if they have a clock and you have a clock, their clock is moving slower than your clock is. So you could reunite, and then you would find that you may have aged more than that person who was moving has aged.
Okay, so can I ask you about that clock, that hypothetical clock that they're holding?
Yes.
Okay, so clocks are a thing we have on Earth, and I don't know what they measure. And I'm wondering if, so you're talking about the clocks that they're holding, like, okay, what do clocks measure, and why is what clocks measuring going to be different for the person going really fast?
Yeah. So what you're asking me is, what is time? And
one time Haley did a really deep dive on Wikipedia about time, I think, or maybe that was me. I can't remember. But
No,
I thought we learned something, but I guess we didn't.
Yeah, the Wikipedia for time is one of my favorite entries. It's fascinating. So.
wow. Well, so you're already an expert, so I should let you take over here.
I need the help though, so please go ahead.
So a clock basically measures just how many times something happens. Our definition of a second is just a number of times that a cesium atom oscillates in energy.
Oh my God. Wait.
So we're just counting how many times things happen.
I didn't know that. I had no idea that a second was actually tied to like some observable thing. I thought we just like decided like, let's just divide it in. We'll divide into 60 because 60 is a hard number to use.
Yeah.
It's not like a 10 or 100. Like okay.
So I'm not sure how the history of that came about. I'm sure what happened was they wanted to divide, they like knew what a year was and a day was, and they wanted to divide that up into some other unit. So they basically had a human version of a second, and then scientists went and wanted to define that in something more quantifiable. So they defined it as however many oscillations of a cesium atom.
Wow.
So the day in a year is our Earth, is relative to our Earth, right? So like it has to do with the sun and the Earth, right? Okay. So when we're deciding that so we're talking about time dilation and deciding that time works faster for some people than others, is there a way to define that without resort to like how we define a year and a day? Because that's different in the rest of space, right? I don't know if that makes sense. Okay.
Yeah, absolutely. So this all goes back to the principle of relativity. So relativity describes why time dilation is happening, describes some other things like length contraction, all the goofy things that happen when things move really fast. And the principle of relativity is that we cannot detect our own uniform motion relative to empty space. From that one statement, we get all of these great things like the fact that the speed of light is constant in any reference frame. So I can explain to you guys, if you're interested, how that comes from that, and then how from there we get time dilation.
Yes,
but
please.
It
takes no math, but sometimes it's a little hard to wrap your head around.
Wait, let me pause you for 1 second. So the whole concept of relativity is that you can only know the speed of something relative to something else?
Yes. So if you're flying on a plane, you don't feel that you're flying. It just feels like you're staying still. To you, it could just be that all the fields and things that you see below you are moving. From your perspective, it doesn't really, you don't feel that as a physical thing.
Right.
So, yeah, everything's moving relative to other things.
Just depending on what your vantage point is. Yeah, okay.
Yes. So I have a picture that I could show you guys, but I know your listeners can't see it, but maybe it would help you ask some questions. Am I able to paste this in the chat or something?
If I'm not sure. And we can definitely put the link picture up on our... Yeah. We can definitely put the picture up on our social media too when we post that episode.
I remember seeing something once where, like, if you were going at the speed of light and you turned on a flashlight, nothing can go faster than it too, right?
Yes, nothing can go faster than the speed of light, not even information.
So your flashlight would be useless.
It would illuminate in front of you. Yeah.
Yeah, it would not.
Okay.
So, but you can. So, am I able to email this to you? Would that work?
Yeah, sure.
Okay,
Yeah,
I'm sending you 2 pictures right now.
Okay. Okay. Everybody got it?
Yeah.
All right, you ready for your physics lesson?
Yes.
All right, we're ready.
All right, so this first picture is explaining why the speed of light is constant. So you can imagine that you want to measure a wave traveling through a slinky. So the left-hand side of this picture is showing a person holding up a slinky. They push in the end of the slinky and they send a wave down that slinky. We have another person that is holding a meter stick up to the slinky, and they're using that meter stick to measure how long it takes the wave to travel 1 meter. So as that compression in the slinky reaches the front end of the meter stick, they're pressing go on their stopwatch. And as it's leaving the back end, they're pressing stop on their stopwatch. And then they know how long it takes the wave to travel 1 meter. But in the image below, we're thinking about what happens if you're running towards the person who sent the wave down. So what if you're moving at a constant velocity? Well, if you're moving, then the time it takes for the wave to get from the front end of the meter stick to the back end of the meter stick is less. So you would measure a faster velocity of that wave if you were moving. The thing that is maybe not so intuitive is that this is not what happens when we look at light. So on the right end of this picture, we have a person who's holding a meter stick, and at the either end of the meter stick, we have a photocell. So the photocell is going to tell us when light hits it. So let's say we send a pulse of light through those 2 photocells. That will tell us, it'll trigger the first photocell when it hits that, and then it will trigger the next one and a little bit of time later, and we'll be able to tell how fast the light traveled through that meter stick. But if the person is running towards the person who sent the light through, what happens? Well, if it's the same as the slinky example, the light should be measured to be going faster. But that's not actually what we find. We find that the light is going at the same speed when we measure this experimentally. And the reason that is, it all goes back to the principle of relativity. It's that the wave in the slinky is traveling through the slinky, so we can tell the velocity relative to the slinky. But the light is just traveling through empty space, so we can't tell when we're moving relative to empty space. So that was a lot that I just threw at you. So how do you feel about that?
Is it just because the speed of light is the cosmic speed limit, like nothing can go faster to it, or is it?
Yeah, I mean, that is why the speed of light is the cosmic speed limit. Yeah.
What if the man was moving at the speed of light in the opposite direction? Still wouldn't matter?
The person who was holding the meter stick?
Yeah.
Then the light would never reach the meter stick, so.
Oh, yeah. Because they'd be traveling at the same speed.
Oh, I meant no, like direction. What? I meant if it was going towards the guy holding the laser, and the laser was going towards the meter stick.
Yeah, you would still measure the same speed of light.
Huh.
Yeah, crazy how that works. So that's not really something that we can intuit because we never get close to the speed of light. So we wouldn't know that things happen. So things are so weird when you move at the speed of light.
Is it proportional too? So like if you go at half the speed of light, is there half the effect, or is it?
Yeah, so the constant that you're multiplying by is the square root of 1 minus v squared over c squared. So c squared is the speed of light squared, and v squared is your velocity squared. So if you're moving close to the speed of light, you have 1 minus a number that is about 1. So you have a bigger effect. If you're just multiplying something by 1, you get the same number back. But the closer v is to the speed of light, the bigger the effect.
Cool.
So, have I convinced you that the speed of light is constant? No matter how you're moving?
Oh, I just believe you.
Yeah.
Okay.
Yeah. I think the speed of light constant thing is just like based on what we know about physics now. Like, if you look at like what we knew about physics 600 years ago, like how much different could it be in 600 years from now? Like, but that won't change.
Yeah,
hopefully, right?
I know. We didn't even know what light was 600 years
Yeah.
ago.
Yeah. So
We
I think
were
that's just like,
guessing.
it's just like the agnostic English major part of our brains. We're like, well, is it really?
Yeah. Well, I definitely, when I first learned about this, I was like, I'll just accept it. The speed of light is constant, no matter how you're moving.
Right. That's where I'm at. I'm like, I believe you.
Okay.
I believe
that's all you really can do.
Well, the next part of this, the fact that time dilation happens is, I think, a bit easier to understand. Just using the fact that we accept that the speed of light is constant. If you have a clock that is moving through space, if a clock is moving, it has to take longer to click. So that is what the next image is explaining. So I can briefly talk about that.
Sure.
So we talked about what time was before and how it's just a measure of how many times something happened, and that's our unit of time. So we can make a clock like the image on the left, that is just a plate on the bottom, a plate on the top, and a beam of light that is traveling between those two plates. And we'll say 1 unit of time is when the light travels from the bottom plate to the top plate back to the bottom plate. So that is our clock. Then if you're in space, but you're not moving, you're just kind of sitting there chilling in space, and you have an astronaut that's flying past you at a constant velocity, you both have this clock and they're synced up. You can see that as the astronaut is moving, the light needs to travel a greater distance to tick off 1 unit of time. It has to not only go up and down, but it has to go in the direction of motion of the astronaut. So our 1 unit of time is going to take longer to happen for the astronaut than it is for us. So time is moving slower for the astronaut.
Oh my God, that was so helpful.
It's actually time and not the measure of time, too.
Yeah. That's so interesting.
How does that relate to how your body ages, though, right? So you have time is measured. I understand why the measure of time would take longer, but given that image. So, but how does that relate to why you wouldn't age?
So so our clock is a time clock, but a clock can be anything. It could be us and how we progress through our lives. It could be a wristwatch. So say like we have a different time measuring device. Maybe it's a watch. Maybe it's just us and our aging selves. We can kind of think of this as a proof by contradiction. So if we did age differently, we end up violating the principle of relativity. So let me explain that. So say you have another clock that's just your regular gear clock, and the astronaut is displaying that clock right on their window alongside their light clock. So we just talked about that we know that the light clock has to move slower from the viewpoint of someone who is not moving. If they can also see the regular clock, then and that clock hasn't changed, that clock is synced up with their own clock, then they're seeing that the light clock is moving slower than the regular clock. And so the astronaut must be seeing this too, that they have a light clock that is moving slower than the normal clock. But they were synced up at the beginning of this thought experiment. So what happened? Suddenly the light clock started moving slower for the astronaut. All the astronaut has done has moved in a constant velocity. And what we know from the principle of relativity is the astronaut should not be able to tell that they are moving at a constant velocity. So the two clocks becoming out of sync would violate that principle. So everything that happens is slower, not just this light clock.
So that would count if your clock was bouncing a basketball, just up and down, because of how you're moving through space, hitting the floor, hitting your hand. It's going to travel. It's going to travel so much because of how fast you're moving that it's going to affect the way that time is perceived. Or no, not perceived, just is. Yeah.
From your perspective, if you're the astronaut who's moving, you won't be able to tell that anything is weird. But from someone looking at you, yes, it would be the same thing no matter what your clock is, whether it be a basketball or light.
Huh.
Yeah, crazy.
So are there real world examples of this? Like, for example, well, I think there's the atomic clock on the space station is like a itty bitty bit off from what it would be on Earth, right?
Yeah, so we've done this. We've measured this. A famous experiment was the Heffel-Keating experiment, which I'm probably butchering the name. And that's where some people had some atomic clocks, and they were all synced up. They threw a couple of them in a plane, and they flew the plane around the world, and then went and compared the clocks. And they found that at the end of the day, they were different. The clocks were different.
So even a plane, wow.
Yeah, so it was a difference of like probably microseconds, but with an atomic clock, you can measure that small difference.
That's so interesting because we, with science fiction and movies and things, like I think we tend to think of this and only really consider it on an enormous scale. Like if I'm way out by Jupiter or something, and I'm using that as an example because I just watched Interstellar the other day.
Nice.
But yeah, like to think of that phenomenon occurring observably on Earth, like all within Earth, is so interesting on something as mundane as a airplane ride.
I know. It's so crazy to think about that. It's a difference that we would never be able to feel, but it's there all the same. And these big cosmological things that we're thinking of can be measured if you can think of a clever way to do it.
Okay, so if I travel around the Earth a bunch of times on a plane, then I will not age.
You'll age maybe a microsecond less than the people.
What if I just keep doing it?
Just stick with moisturizers, Amy.
I gotta pull a Mary Gay and just keep being in the plane.
So the speed makes sense because of what we've just talked about. Can we talk about how gravity and like big mass affects time? Because that's where I get more confused, I think.
Okay, so the clock experiment, or the experiment that we did where we put some clocks in a plane and flew them around, it's not so simple as the case that I just explained to you because there's other factors coming into play there. So I explained special relativity to you, but there's also something called general relativity, which is a lot more complicated and takes into account that we have a time dilation associated with big gravitational fields, and we also have time dilation associated with accelerating reference frames. So the fact that the plane had to accelerate to take off and decelerate to land, and the fact that it was not experiencing as much gravity when it was in the atmosphere also play into that. So when we were comparing the clocks to prediction, we had to account for both of these things.
Could you also... Yeah, sorry.
I was just going to say that so if you're really close to a giant gravitational object, you will also experience time dilation. So time will move slower for you than someone who is further away from that object.
Oh, that happens in Interstellar.
Yeah, that's a big thing in Interstellar.
Yeah, I was going to ask. So I think we all learn in school, at least I did, like gravity is like things falling to Earth, but it's more than that. So could you give like a better definition of gravity?
Of gravity?
Yeah.
Well, gravity is a force. Well, there's a gravitational force. So there's some fundamental constants in the universe. One of them is the speed of light, which we just talked about, and the other one is this gravitational constant. So massive bodies are always attracted to each other. And this goes into what we think of as space-time, which I'm not sure if I can really do justice to that, but very massive objects warp space-time. And that's what causes this general relativity and time dilation due to gravity.
Are there any theories as to why? Or just like, just because?
There's theories that explain it. I don't know how philosophical they get. I mean, doesn't it all go down to like, why are the laws of the universe what they are? They just are. And if you go beyond that, I think it's more of a philosophical question. But interesting to think about.
So I want to pose another question from one of our listeners. Ronnie on Instagram wanted us to ask you, are there any kind of pop culture treatments of this issue that you sort of make you roll your eyes, or that you're like, nah, that's not real? Anything that you want to debunk that we see all the time in movies or anything like that?
You know, with time dilation specifically, I feel like it's already kind of wacky enough that it fits into science fiction pretty well. There's definitely, I'm always watching popular movies and TV shows and thinking, okay, well, maybe you should have gotten a physicist on board for that one. But Interstellar specifically, I've never seen it, but I have kind of gathered what happens from other people, and I've talked to a lot of physicists about what they think of it. And, you know, physicists generally enjoy that movie. I've heard that the visuals are really accurate, although the ending sucks. From a physics perspective, I'm pretty sure Matthew McConaughey somehow leaves a black hole, and that's a little bit iffy. But you know, the rest of the movie, my undergraduate advisor gave that movie a C in terms of physics accuracy, which is pretty decent.
That is better than I would do on an exam about physics and the accuracy of that. Interstellar is doing better than me. Yeah, I read that they definitely did a lot of consultation and research with actual physicists in the production of the movie. So, you know, I had seen it several years ago and didn't remember it that well. And then since somebody was, I think, pretty much asking about that movie, I decided to rewatch it. And then I found out that it was like fairly well researched. And then I guess, like you said, that time dilation has room for some artistic space to play, I guess.
Yeah, I mean, there's a reason it's so popular in science fiction. It's just kind of a fun concept and fun to try to wrap your head around it.
It is, and it really sets up a opportunity for like kind of the tragedy of space travel. Like, you are leaving behind everyone you knew. You are potentially leaving behind your whole family, and possibly coming back to a world that you won't recognize, which is what happens in the Forever War that we're going to talk about for our December podcast episode. And that's exactly what happens there, is the main character leaves to go off and fight a space war. And then by the time he comes back, Earth society doesn't look much like what he remembers.
And sometimes you leave and come back and the apes have taken over.
It's so compelling. That too. Anything can happen when you're going near the speed of light. I mean, not anything, but
that scene in Interstellar, I think it's in the middle of the movie, and the ending is weird, and love is not a dimension, whatever. But like, they decide to go down to this planet that's being influenced by a black hole, and there's huge waves, and for the purposes of the movie, they're like, every hour on this planet is going to be like 7 years in like real life or whatever. And so they go down and they get in trouble, and it's like 3 or 4 years, and then they get back on the spaceship. And they've left a man alone there for 20 years. And then Matthew McConaughey checks his answering machine, and there's like 30 years of like life updates from his kids and grandkids, and it's wild.
I mean, that's why the human aspect, we're always so drawn to the human aspect. So when the science and the humanity can intersect, that's what the stories are all about.
I haven't seen that movie, but I feel really bad for the guy they left on the spaceship.
He makes it a little bit better because he goes into hibernation, but like he's aged at least 15 years.
Okay, so he doesn't just wander around the spaceship for 20 years.
He was up there working too. He didn't fully go into hibernation. He does some of the time, because he's like gone from a young looking man to quite gray when they get back on the ship. So he spent a lot of time like doing math by himself, and he seems sad about it.
Aw.
The first time go ahead. Yep.
Oh, I was going to say, well, Emily, I think that these are 30 minutes, so we don't want to keep you any extra time. But
I mean, I wouldn't worry about it. Ask your questions.
Okay. Well, we had other questions in our list that stem from the Forever War. Like, I'm betting that this is a question that Amy put in there that says, what would 23 Gs do to your soft parts?
Oh, yeah. That's a fun one.
Have you read the Forever War, Emily?
I have not. But I looked up the Wikipedia so that I could at least understand what kind of physics they're using in it.
Yeah, so when they travel, the narrator tells us a lot about how many G's they're doing, and then if they're over a certain amount, they get in these what do they call them? Acceleration couches or something, and they're like zipped into a pouch, a life support pouch, and it's filled with goo, and I guess the goo is supposed to absorb the pressure. And sometimes the suits go awry, and then the people absorb the pressure.
Which apparently, by the way, that was based on real life. What would happen if you were an Air Force pilot and you were going really fast in your plane and there was a crease in your suit? It would tear and do weird things to you. So that was like a real thing that happens.
Yeah, so fighter pilots are trained to withstand more Gs than us normal people can. And sometimes they wear special suits to try to account for that. So we can talk about how many Gs is normal.
Yes.
I don't know.
Well, how are there Gs in space too?
So yeah, Gs is just a unit of acceleration. So 1 G is the acceleration due to gravity on Earth. And we can measure any acceleration in terms of that, just as multiples of the acceleration we have on Earth.
So 1 G is Earth gravity?
How much acceleration? Yes, 1 G is Earth gravity. We can only really withstand about 6 Gs before we just pass out. A roller coaster usually has 4 to 6 Gs. But fighter pilots can withstand 8 to 9 Gs, but only for a couple seconds. The problem here is not that you get squished from the force, it's that the blood in your heart can't travel to your brain and you just pass out and die. 23 Gs is doable. There are people who have experienced that for a couple seconds and survived.
Wow.
But that depends on the orientation of your body compared to the acceleration.
Oh.
We're better at experiencing accelerations that are perpendicular to our spine. So eyeballs out or eyeballs in is the term that people use when they describe that.
What's the context of someone having survived 23 Gs for a couple seconds?
I do not recall. I remember I was looking this up and there were some people who survived car crashes.
Oh, okay.
Especially like NASCAR they have, but it was for a very brief amount of time.
So if you were going very fast and slammed into another vehicle or a wall or something, then that would cause you to experience increased Gs?
Yeah, so G is just acceleration. So if you're going really fast and then you immediately stop, then you've experienced a lot of acceleration. Acceleration is a change in velocity. So if you're speeding up or slowing down, you're accelerating.
What? So if you fall from a plane and you're plummeting towards the earth, would you only experience 1 G?
Yeah, only 1 G. The force of impact is quite a bit more than 1 G.
Interesting.
So when you go from moving really fast, so you won't accelerate indefinitely because of air resistance. You'll reach a terminal velocity. But when you go from that terminal velocity to hitting the ground, you accelerate very quickly from going very fast to not going at all. And that is the force that kills you.
That's like the joke. It's not the fall that kills you. It's the stop at the end.
Exactly.
Let's see. Amy, did you put this video about the 10th dimension in the Google Doc?
We can ignore that. It's.
I remember you talked about it when we read the 3-body problem.
It's tangential. It doesn't really have. I decided after I put that in there that doesn't really have anything to do with what we're talking about. So.
I did watch the first part, and once they got to 5 dimensions, I was like, well, all right. Watch part 2.
I watched it. It was a pretty good video. I mean, it was a good way to visualize some of this stuff, although they bring quantum mechanics into it at some point, and then they got a little iffy. But it was pretty good.
That might be a good segue. So they travel basically via wormholes, I think, in this book, but they call them collapsars. Okay. So could you talk a little bit, like, are wormholes a theory? Are they something that might really happen? Or What's the state of the art of wormholes right now?
So you asked me before about science fiction treatments of this that are that make me angry, but it doesn't really make me angry. But wormholes are definitely stretched in science fiction. They are theoretically possible. They very well could exist. If they do exist, they are very tiny and they are unstable. So if anything tried to enter them, it would destroy them. We have been thinking about ways that we could make a stable wormhole. Theoretically, could we make one? And the answer is not with any of the physics that we know right now. It would require some exotic matter that we haven't heard of yet. So maybe someday we'll discover that matter and can make a stable wormhole.
Is the concept behind a wormhole just like a tunnel through some sort of space-time, like as if space-time was a thing?
So a good way to think about it is using that video. That was the 10-dimension video. So that video explained how we have 3 dimensions, and the way that we get from one point in our 3 dimensions to another point is by traveling through the 4th dimension, time. So it's kind of like, okay, we're in our 3-dimensional space, and we could fold through this other dimension and get to another point in it without actually having to travel through all of that space.
It's a shortcut.
It's just a link between 2 points in space. Yeah, shortcut.
That's like a Tesseract in A Wrinkle in Time. If anybody's read that, that was one of my favorite books as a kid. That's what it is. It's a wrinkle in time. You just fold the time.
Yeah. I've definitely heard wormholes described as a wrinkle in time before.
So wormhole and black hole, not the same thing.
No, a black hole, though, is one of the ways that we think that maybe a wormhole could be created. Black holes are just collapsed star. So I saw the word collapsar when I was looking up the Forever War. A collapsar is just a collapsed star, but I think what you would specifically need is a collapsed star that has turned into a black hole.
Oh.
Why is it called a wormhole? Is that a science fiction name?
That is probably an interesting piece of history that I don't know.
Yeah, I guess since it's made up, it probably doesn't come up in your field of study.
I mean, I've heard physicists use the word wormhole.
Oh, really?
Yes. It's not the technical term, but, colloquially.
I think it's because if you look in dirt, like worms actually leave holes between 2 discrete locations. So it might be just based on farming.
The first Google result says that wormhole is from the 1590s. It's a real thing, a hole made by a burrowing insect, but the astrophysics sense of it is attested from 1957.
Interesting. We're learning today.
Yeah. So do you think, Emily, that this thing in the Forever War where they are in like a goo-filled bag, would that protect someone from the acceleration that they describe in the book? Or would a goo-filled bag have no protective properties?
Definitely if you were in a capsule that somehow had an opposite force that would counteract this acceleration, that could protect you. Maybe somehow the inertia of the goo keeps you from accelerating so fast. Off the top of my head, to me, that sounds like it wouldn't protect you. You would need something a bit more complicated, but maybe it helps.
There was an explanation from Haldeman on a Reddit Q&A that I read where he said that part of what that happens in the tanks is that they're trying to pressurize people so that they are equivalent basically to the outside pressure, so they didn't mush up. Does that make sense?
Physically, I guess I would like a little bit more context before I could comment on that.
Maybe it's biochemistry. I don't know.
It definitely makes sense to a reader, right? I can imagine if you wrap me in a big foam rubber bubble and drop me, the foam is going to insulate me from the impact of the ground. So I think it's the same kind of thing. It's just to a sort of ridiculous extent, which is what all of science fiction really does, is it takes something that's like plausible and carries it out to, maybe ridiculous isn't the right word, but to an extreme. So it makes some sense as a reader.
Yeah, I mean, suspend your disbelief. That's what I always do.
Yeah, he also spends, I think, too much time talking about it. Like, he could have not brought it up and I would have been just fine.
That tells me he researched it and he wanted you to know that he researched it.
To me, it was kind of
interesting.
It was kind of like people saying, like, well, if an elevator's falling and you jump at the last second, you'll be fine. Like, it was that kind of energy. So.
Yeah, I mean, it would have an effect. I can't imagine it protecting you from 23 Gs, but perhaps.
All right, I've got a theoretical question about traveling at the speed of light. So you could travel at the speed of light for a long time. Would it be possible to get to the end of time? Like, could you get to the end bang if you keep going forever?
This is just a yes or no question. Yes, you can get to the end of time, or no?
No. Well, you're traveling through time, right? Like any of us, if we wait long enough, I guess we'll live to see the end of time.
Well, because at one point they were talking about if they go off in the wrong direction, they could come back 140,000 years later. So I was like, well, but eventually maybe the universe won't exist. I don't know. But like, just when you start talking about like these big chunks of time, I was like, well, shit, where does it end?
Yeah, I mean, that's another philosophical question. So we know that the end of the universe, or how physicists think it will end, is a heat death. Everything will just expand, and all the energy will just kind of even out throughout the universe, and it will just be big nothing expanse of space. The universe is expanding.
Emily, please go get your
sounds very
PhD
dramatic.
in philosophy.
Okay, we'll do.
So there's a couple places in the Forever War that I really could not wrap my head around. So the premise is that humans are at war with this alien species called the Taurans, and nobody really understands why, and that's kind of part of the commentary since Haldeman was a Vietnam veteran. But there are places where the narrator tells us, well, we don't know which Taurans we're going to get. I think I said Terrans. I meant Taurans. We don't know which Taurans we're going to get. They could be the ones who show up for this skirmish could be future Taurans, and so they have technology we couldn't have anticipated, or they could be past Taurans and they've got like the equivalent of sticks and rocks compared to us. And that is something I had a very hard time wrapping my head around, that they could physically encounter each other but be from different points in time. So is there any theory underpinning that makes that, I mean, obviously it's not real, but is there any like scientific theory behind that?
I guess the Taurans that you would encounter would just depend on how they are moving relative to you. So how much time dilation has happened.
Okay.
That's my immediate thought when I think of that. So maybe there's different groups of Taurans that are moving at different speeds, and that maybe just explains it.
Yeah, that makes sense, I guess, because if they're just sort of sitting on a planet waiting for the Taurans to arrive, and they're with the static technology that they had, and Taurans are flying around in space, then I guess I don't know. That one was one that just really, I sat with it and thought, and I was like, okay, I'm just not going to get it. I'm just not.
Yeah, sometimes if I watch time travel movies too much, I get a headache, but I kind of like that headache, so...
Yeah, I am always, whenever there's time travel in any piece of media, I'm always like, okay, how is this a paradox? How can I poke holes into this?
So I love that Doctor Who, with that, the doctor always says, paradoxes by and large resolve themselves, and they just keep moving. He always says that, and it's like, okay, that's fine.
Yeah, I'm okay with that.
Yeah, I honestly find that a lot more fun than trying to make up something that will work, because I don't think you can do that in like a 40-minute television program.
When you try to make it logical, then your viewer is also going to try to make it logical, and then if they can find holes in your logic, it kind of ruins the experience. So I do like it when they just say, "Yep, this is what it is," and I say, "Okay."
Anything else, you guys?
I am thoroughly confused. I'm good to go.
Yeah, I feel like I fully understand all physics now.
Great. That was the goal.
Well, Emily, I wanted to ask you too, do you want to talk a little about how you got interested in this field and how you started working on what you're working on?
Oh boy. I mean, that is a question that I should really know the answer to. But I guess the answer is it just really worked out this way, and I'm glad that it did. I was interested in science in high school, and then I thought, oh, we'll give physics a try in college, and I just really loved my classes, and I really loved my professors, and I think a lot of it had to do with the environment and the culture that I was in at my school, and then I just didn't want to stop learning about it, so I went to grad school, and here I am. Woo-hoo. And I'll be learning about it for a while.
I love that. I think that's a great story because the thing that comes up for me when I hear that is like, just stay curious and stay open to things.
Yeah. You start learning about it and you realize that there is just so much that you don't know. And I'm just not satisfied yet. I need to, at least get some of these things worked out in my head.
Yeah, you can probably keep going until the end of time, right? And there will still be interesting stuff to learn.
Yeah, it will never end. I will always be like, oh, I should just, take this class.
I will learn until the galactic heat death.
Exactly.
There are definitely worse ways to spend your time,
Yeah.
All right. Anybody have any other questions?
No, thank you so much, though, Emily.
No, thank you so much.
Yeah.
Thank you guys. Hey, feel free to send me an email if you want to straighten any of this out. I know usually the first pass doesn't stick. You gotta, go over it a couple times.
I kind of want to just keep you on a retainer for the rest of our
votes. I'm going to be listening to this a few times at least.
Sure. I mean, I'll be available for comments.
We can just make like a monthly donation to Skype a Scientist and then check in with you.
Sure.
Emily, what's going on here? Do you want to join us for 5 minutes for this podcast? Well, thank you. This has been so fun and super helpful. And we're really grateful to you for sharing your time, especially when you've got time off from school and work and everything that you've got going on, that you gave us an hour of your time. So thank you again.
Yeah, no problem. It was fun.
So while you were listening to that, 30 years passed on Earth.
Something like that. I keep reading about time dilation. I've been watching more videos, and I'm more confused than I was 2 days ago.
I feel sort of outraged when I think about it too much.
Part of me is just like, okay, so a clock slows down. I get that because distance, but like, why is time slowing down?
I don't know. It made so much sense when she explained it, but I still don't. I'm still outraged by it.
It doesn't seem right, and it doesn't seem fair.
No, it's insulting.
It isn't right. It isn't fair.
Well, and it goes back to what you said about, are we sure it's the cosmic speed limit? And I think right now it is for what we know, but 600 years ago, we know jack shit about anything. But hubris, I guess. What do I know?
Well, as long as we don't think we know everything, then maybe we can avoid hubris.
Well, that's where I think this comes from. It's like, how do you know it's the cosmic speed limit?
Well, she was very upfront, like, we don't,
Yeah,
but
that's true.
For anything we can measure,
That's true.
it works. And we can't, there's nothing else we've observed, so.
I have to admit that I did not understand that. She was talking about how the person in the plane can tell that his clock is slower, and since he can tell his clock, or can't tell his clock is slower.
It would not be something that is meaningfully noticeable. It wouldn't be something noticeable, but when they use like an atomic clock, they can tell that there's out like 8 decimal places or something. There's a difference that can be measured by very, very, very sensitive instruments.
Right.
But you would never notice the difference.
And so when we asked why the person wouldn't age correctly, like I get the clock thing, but like the person aging still throws me because it's like,
a clock is a simple, the light clock was a simple function. The light bounces up and down, or the light has to bounce effectively in like a Z or an M or something. Like that makes sense. Cellular function, I don't understand. But I mean, is everything just movement? I don't know. Everything, all atoms are vibrating all the time. So maybe that's.
Oh, I had
jazz hands.
Yeah, I had a breakthrough about gravitational time dilation. I get it.
Oh. Let's have it.
I can't explain it to you, but I understand it in my mind. Okay, so there's videos online, and like when you see like the pictures of space-time curved, it's like, you see like the green and black netting.
Yeah.
I think what space-time is just like a blank slate, and then everything that has mass, so it's like everything in the universe, gets superimposed in that, and that's what creates gravity.
Check our Instagram for the images that Emily shared with us during the conversation.
I did find them helpful, for sure.
I did too.
Definitely did.
Especially the clock bouncy lighty.
I was dubious at first, but I was like, okay, I get it. All right.
She did a great job explaining it.
She was fantastic. Yeah. Thanks, Emily.
And if you enjoyed this episode, you can donate to Skype a Scientist.
Yeah.
And if you need a scientist in your life, you can sign up for Skype a Scientist.
Apparently they're great for teachers.
Yes.
It's so nice it exists. I'm just like happy.
Yeah, I think most of what they do is talk to classrooms. And if you have a group where you want a representation for a specific underrepresented demographic, you can note that, and they'll try to match you with somebody who matches the demographic interest of your group. Like we specifically asked for a woman scientist, and so they matched us with a woman scientist, so that was cool. And there are a variety of groups, underrepresented groups, that you can ask for.
Maybe one day someone will invite us to talk about the terror to a class.
We're experts on so many things now. Having read the Three-Body Problem, having talked to Emily, and having read the Forever Or, we've got quantum mechanics, we've got computer programming, we've got time dilation.
We've got
do a lot.
We've got Western maritime exploration.
We've got Antarctic exploration.
We've got both poles.
Both poles represented.
Both poles and New England whaling.
Horses.
Star Wars.
Birds.
Amy, you got birds?
You know a lot. You know a lot about birds.
The law.
If you need metal, you can talk to Kevin.
That's right. Watches.
Mm-hmm. Watches are kind of related. When I was going down a Wikipedia wormhole, pun intended, last night, it gets into chronometry, which is like the art of measuring time.
Ooh.
It was fun. So
horology.
Kevin, I did kind of wish that you were on there when she was talking about the light clock in space. I thought you would be really interested. And when she said a second is actually the physical measurement of the vibration of a cesium atom, I was like, pardon?
My whole mind was blown.
And I was like,
God.
So but also like a Kmart clock too. Time can be measured with a basketball.
I guess we just all agreed what a second is now, and so you can make a clock do a thing.
Yeah. Well, so there's a lot of time that's been based on like the Earth, but then even everything is standardized with science. So like a meter is like how far light travels in like 1/9 millionth of a second or something like. So everything has a way to be measured, but we don't think about that in real life. It's just 1 second.
I didn't know that about a meter.
Mm-hmm.
Say that about a meter again.
So how's like the SI, like the scientific standard unit of a meter, like how they describe it is not just like 36 inches or whatever, or 100 centimeters. It's the distance that light travels in a certain period of time that's really small.
That seems so extra, doesn't it?
Now they're just being silly.
Well, so that's why I liked when she was like, she's like, do you want to talk about science or do you want to talk about philosophy? And I was like, the philosophy stuff's more fun.
I mean, it seems hard to talk about one without the other, really.
Yeah, but I think
when you get too far down into science, it becomes philosophy.
well, exactly. And that's what I like. But like, if you keep it surface level, it's like, well, a second is just this. And then like a pound is really whatever this is. So,
I mean, they could have picked anything to make a second. I mean, to make that unit of measure.
But why cesium?
Yeah, that's what I'm saying. It seems maybe that fit nicely into the units they needed to create a day.
Yeah.
Or an hour or whatever.
Well, I bet if you look up a second on Wikipedia, it'll tell you.
Again, I'm gonna
Haley, get back to us.
I'm gonna once again. I reread the Time Wikipedia article.
But you need to go to seconds.
Second, yeah. I mean, it's
the seconds Wikipedia entry.
It gets very granular, and it's fascinating.
Emily did say we could reach out to her if we have more questions.
She did.
But about this, she's like,
I don't want to abuse that. I'm like a little like I think once I pop, I can't stop.
It's weird to slide into someone's DMs about space.
Dear Emily, about those seconds.
Hey, you up? About the cesium.
Hey girl, what are you doing?
I got this question about horology.
You got time for time? Oh, okay. All right. I think that's our outro.
Yeah.
See you later, everyone.
Okay. Bye.
Bye, listener.